My name is Dan Walsh. I work for Red Hat. I actually lead the container team at Red Hat. So at Red Hat, most of the container effort is done underneath OpenShift. And so OpenShift is Red Hat's Kubernetes, enterprise version of Kubernetes. My team does all the stuff underneath Kubernetes. Okay, matter of fact, when I leave the host, I get a little confused. So this talk is going to be talking about containers. And mainly about container security. So let's get started. So first of all, rules of this talk. If anybody saw me talk yesterday, you know that audience must say all text that's in red. Everybody got it? All right. All right, so the talk is on container security. Okay, that's what the coloring book is for. So the coloring book actually describes container security based on the three pigs, and if you're not from the United States, this might be inappropriate for some countries, but it's anyways. So this container coloring book. Okay, so when we do this talk, we're going to be talking about we're going to go back and forth between pigs and applications, but really what I'm talking about is a service here. So one or more services, if you're running multiple services on a system and one of the services gets eaten by the wolf, then how do we protect the other services from the wolf, right? So we're going to be, every time we talk about pigs, think of that as being an individual service. So the interesting thing about container security, what we're going to be looking at is where should you run your containers, or in the pigs analogy, where should the pigs live? All right, where should the pigs live to be most secure from the big bad wolf? So I start out by saying that the most secure way to run your containers is actually in separate physical servers. The more isolated you can make these servers from each other, the better. In the government, in the United States government, there's this concept called air gap security, where they don't even allow networks between the services. So really what you want to do is run each one of your applications on separate physical machines. That's the most secure way to do it. And the way I can prove that to you is how many people in here have had a machine in their company or environment hacked? Okay. And what'd you deal with that? How did you deal with that? Right, you reinstall it, right, from a known good backup. And of course, you all have known good backups because you know exactly when the hacker got onto the system. So we reinstall from a known good backup. Did you then reinstall every single other machine in your entire environment, every machine that's connected to the network, to the machine that was hacked? I don't think you did. So therefore, you at least believe that if a hacker gets into one physical machine, you don't have to reinstall every single machine in it. So that's like pigs living in separate houses. So now let's go to the next level. So we're going to move the pigs, we're going to move the pigs to a duplex. So now the pigs are living in a duplex, and that's the second most. And a duplex is very similar to virtual machines. Okay, so in a virtual machine, you have a very small part of the Linux kernel shared between the VMs. So each VM has very difficult access to break into the host machine and then get from the host machine into another VM. So the second most secure way to run your applications is on separate virtual machines on the same host. KVM has been around since 2008. I know of two vulnerabilities where virtual machines were able to break out of the KVM environment in 10 years. Both of those, by the way, were blocked by SELinux. But anyway, so over 10 years, there's only been two known breakouts. So the next most secure way to run your, or to have your pigs live is to have them living in a hotel room or in an apartment building. And this is similar to, this is what containers are. So containers is like living in a hotel room or an apartment in that there's a single point of failure. Okay, so the front desk. So if you basically get a control of the front desk, you can get access to all the keys, and then therefore you can get into each one of the apartments. In the container world, if you can basically subvert the Linux kernel, right? The Linux kernel is shared by all the containers. And what I'm talking about here is traditional containers. I'll be talking about some advanced security features towards the end of the talk. But in the traditional, what everybody thinks of as the Docker container, they're basically sharing the host kernel, so that basically if you find a bug in the host kernel, like Spectre and Meltdown, you can take over all of your containers. The containers can break out and take over the machine. So the next one is probably the way a lot of you guys run your services right now, is you run multiple services on the same machine at the same time. Okay, and to me this is like living in a hostel. So the pig's in a hostel. And that, if you're running a web service and a database service, same machine, same time, the web service gets hacked, then it's fairly easy to, attack the database at that point. And then, of course, for those of you that turn SELinux off, that's basically like pigs sleeping in the park. Okay? And for those that don't know, there's a website that talks about me crying every time you guys do set and force 0. Okay, so the funny thing about that presentation, the presentation I've given so far, is it makes containers seem insecure, right? Because they're not as secure as separate physical machines, and they're not as secure as VMs, running your processes on VMs. But if I had done this presentation the exact opposite way, it would give you a different impression, right? If you just take two servers running on the same physical machine at the same time right now, and you put them into containers, you skyrocket the security of those services, right? You make the wolf's job of breaking out of that container way harder than if it's running on the same physical machine at the same time. So just think about that. So containers are sort of a middle ground here of security, right? A lot of times when I give my talks, I think I give people the impression that containers are bad for security. They're really good for security compared to what most people do with multiple services on the machines at this time. The other thing to understand here is that this is not a zero-sum game. There's no reason that you can't run all of these technologies together. You can run your containers inside a separate physical. You can run containers in separate physical virtual machines on separate physical machines. So it's basically using all the tools that you have together to basically pick where you're going to run your applications. I would advise, if you're running web services in your environment, you put them in separate containers on potentially separate physical virtual machines inside of your DMZ, and then you take your databases and you put them inside of containers on separate virtual machines somewhere else in your network. So think about putting all these technologies together. So what is the beauty of containers? Containers, when you run them, they give you better resource controls than virtual machines. But the really big thing about containers is most of you guys out here don't run operating systems just for the sake of running operating systems. Although from Red Hat, I'd like it if you did. And the more operating systems you guys run, the more money I make. But the basic idea is, right, your goal is to run applications. In the container world, you're managing applications, right? The application is inside of the container. As soon as you start to manage virtual machines or physical machines, you're managing operating systems. So if you take every single one of your applications and put them in a separate virtual machine, you end up not only managing the application, but you manage the syslog and the init system and the backups and everything else of that. As soon as you start to put them into containers, you start to outsource that to the virtual machine then has to manage the logs and stuff like that, or out to some higher level tool like OpenShift and Kubernetes. So containers overall are a good thing for security. So we've chosen that we're going to put the pigs into containers, or else this talk would be over. So now we're going to choose where we're going to make what kind of container, what kind of apartment building we're going to put these pigs into. Okay, and the first apartment building, of course, is going to be the house made of straw. So a house made of straw is probably what a lot of you guys are out there doing right now, which is basically doing a homegrown environment. Red Hat's biggest competitor in the container world, homegrown. Okay, we compete against homegrown all the time because all you sysadmins that are out there right now, you guys like to build your own stuff. Okay, which is good, but I have a feeling you guys work for banks, or you work for schools, so you work for the government, and your primary business is not in the operating system business. So really what you're doing here is you're building a house of straw, in that you have to manage the entire environment, security updates of the libraries, everything. You're in charge of it. So the next level up for a house of straw, of course, is a house of sticks. And the house of sticks is basically based on running containers on a community platform. And what I'm talking about here is you get some support cycle, right? You run it on Ubuntu, Fedora, even CentOS. You're getting some security updates. But on most of these, there's a very short lifespan. And everybody right now says containers are the cool thing. I'm going to run them forever. But I always go back to a few years ago, I was giving a presentation to a company, and I said, you know, RHEL 6 has some really great features. And the person looked across at me and said, I run 40,000 machines on RHEL 5. I will upgrade RHEL 5 2 years after Red Hat says they won't support RHEL 5 anymore. So as we move to containers, you guys are going to slowly but surely realize that these containers are going to get older and older in those containers, and all of a sudden you're going to get nervous about upgrading. So you really need to have a secure, you know, you don't want to be upgrading that operating system every 9 months, right? That operating system that runs it as you get the containers. So you really need something like the house made of brick. And of course, here's my sales pitch right now. The house made of brick is RHEL, okay? But basically, you know, you have a company behind it that's willing to support the operating system that you're going to run these applications on for the next 10, 13, 15 years, right? Now, when RHEL 7 came out, you know, 5 years ago, I said, well, RHEL 7 is going to outlast me, and it probably still will. But RHEL 7 will probably be around for 15 years. You know, RHEL Next, which I don't know if we're still allowed to call the next number that comes after 7. We've been blocked inside of Red Hat for a while now. When that comes out, that's going to be, you know, around, well, I'd probably be dead before that thing's not supported. So most of you guys came to this talk actually to hear this section of it. So this section, it is, you know, how do we secure these containers? You know, the wolf has broken into one of the containers and taken it over. How do we prevent him from attacking the other pigs in your apartment building? So a few years ago when I first started doing security talks on this, I quoted my semi-famous quote, or at least in my little small pond, is that containers don't contain. Okay, and what I meant by that is, you know, you have the single point of failure. You have the containers running on the kernel. And really what I was trying to stress here is, if you're going to use containers, don't think of this as like the holy grail of, oh, I put my application inside of a container, I can start doing bad practices. All the good practices that I've done over the years for securing applications, I don't have to think about those anymore because I put them in a container. So what do I mean by that? Well, usually I say, do you care and should you care? And if you maintain the good security practices, if you continue to drop privileges as quickly as possible. But stop, I don't like to say that. I like to say stop running as root. So this is not I got rushed in here at the last minute. I don't have the right presentation. But I wrote an article saying all containers should run as non-root. Okay? What I mean by that is we have built up this infrastructure where everybody expects containers to run as root. Does a web service need to run as root? No. Databases? No. Just about every application you ever run in a container environment doesn't require root. The only applications that require root are things that are modifying the operating system. And usually when we're putting containers together, we don't want them modifying the operating system. So why do we start out as root when we're doing the containers? There's this company called Red Hat that's screwed up containers. Okay? It ain't Red Hat also, it's Canonical. And it's every single distribution that ever put together an operating system basically went with the assumption that an admin is going to install software onto a system. That system is going to be started by the init system, systemd or something else, and it's going to start as root, and then it's going to drop privileges. So most container software is written with the assumption, right, you're just using distribution software. So I install the version of Apache onto a system or Nginx, and it says, I'm going to bind to port 80. That requires privilege. So all this code is written to basically make Apache start up, drop all its capabilities, bind to port 80, drop all its capabilities, and become non-root. But when we go to containers, we should be doing it, just run it as non-root to start. And if we could do that, so little story on that, OpenShift out of the box, when you run our OpenShift Kubernetes environment, it runs all applications by default as non-root. Okay, and this is probably one of the things that people least like about OpenShift, because they can't grab any image off of any container registry and run it because they need modification. All right, so because most of those applications, if you went out to Docker.io right now, I would bet you 95% of those applications assume they have to run as root. So that's a major, major problem we have. So if you can basically get your environment to make the assumption to run as non-root, then the rest of this talk doesn't matter. Okay, well, it matters somewhat. But anyway, so if we can just get to the point where we could run applications as non-root, it would be a great advance. So we want to drop privileges as soon as possible. We want to run services as non-root whenever possible. We want to treat root inside the container the same as root outside of the container. Just make that assumption. If I give you root, you can do whatever you want on the system. So a few years ago, a fellow engineer at Red Hat basically came out with this statement, and Docker is all about running random crap from the internet as root on your system. And I think that's pretty much what it is. Okay, so many people go out to, I don't know, there was some stat, there was some hack that got put onto Docker.io, and I don't know, it was 18,000 people downloaded the hack onto their system, and basically they were from random, crap containers that were all infected, and they just installed them on their system. All right, so don't do that. Only run containers from trusted parties. All right. Pretty simple, right? No one goes and gets an RPM from hackme.com and installs it as root on their system. So why are we doing that with containers? So why don't containers contain? Well, the number one reason is everything in Linux is non-namespace. When we talk about containers, the basic concept is the kernel provides these features called namespacing. So namespaces is what gives you that virtualization feel. But things like if they were comprehensive, these namespaces were comprehensive, we'd call it KVM, so you'd have full virtualization. But basically, kernel file systems, right? So things like /sys, /proc, sysfs SELinux, sysfs Cgroups, dev kmem, devices, right? General device nodes on the are not basically separated. So basically, if I can actually write to anything on the system, any one of these, I can take over the kernel. So what we do inside of the operating system is we spend, inside of containers, is we spend a lot of time just trying to prevent a root process from being able to do these things. So let's go overview of security within OCI containers. So what we want to do here is we want to protect the host kernel from processes within the container. So I did have that up here. So this is the article I wrote on just say no to root inside of containers. It's up on opensource.com, but if you just Google that, you'll find it. This presentation will be made available afterwards, and all my presentations are up at my people page on Fedora Project. Oh, they do. Oh, well, funny you should bring that up. So we want to protect the kernel file systems. So we have these kernel file systems /proc, /sys that allow you to modify it. So what we want to do is we want to run those as read-only. So it turns out that even though almost no processes need to actually manage the operating system and write to these kernel file systems, a lot of them need to read them. Right? So almost everything, there's tons and tons of tools that do things basically equivalent to the PS command. I'm not sure why, and I've seen it over the years with SELinux. But basically, there's lots and lots of these processes all go out and read /proc or /sys, and they're looking for certain kernel parameters, things like that. So they need to be able to read these, but they don't need to be able to write them. So the first thing we do in container security is we mount all of the kernel file systems read-only. The next thing we do is there's certain kernel file systems that leak. Right? Kernel wasn't designed thinking about this, so there's certain kernel file systems that leak information into the containers that could be used, basically the containers could use that to, reveal other parts of the system. So there's a whole bunch of kernel file systems that we actually mask out, which really means we're mounting a tempfs on top of them, and that's mounted to read-only, so there's nothing much you can do with it. So if I have all these kernel file systems mounted, I'm running as root inside of a container, I have all these kernel file systems mounted read-only, what's the first thing I'm going to do as a hacker? Remount them read-write, right? So the next thing we need to do is shrink the power of root. So we have to look at root and basically shrink the power of it. And the way we do that is we take advantage of, we want to stop root process from remounting the container, the file systems, and there's a thing called capabilities in the Linux kernel. It's been around since the 1990s, okay, Linux capabilities. Some of you people have probably heard of these, or you've heard of like setuid and setgid. So what they did back in the 1990s is they wanted to take this all-powerful root and start to strip away some of its powers. I'll basically break it down. So the first thing they did is they took an integer, right? So they had 32 fields, and they broke up the power of root into 32 logical blocks. And so the capabilities looks something like this. So this is a bunch of capabilities that actually we removed from the system. So the ability to load a kernel module, the ability to change the resource, sysnice to set, basically to make my process more important than your process. Mac override is changing SELinux policy, writing to the audit log system. So there's a whole bunch of these capabilities that we can actually strip. Again, almost no process, even a process that starts as root, your Apache process is not going to do these things. Okay, so we can actually start to strip them. So we started out, we said there was 32 capabilities originally. By the way, there's 64 now. But basically when they started out with 32 capabilities, you can imagine that right away they said, oh, let's get ping, right? That was, create an ICMP packet, we'll give them a capability. Bind to a port less than 1024, we can give that a capability. So they started going down, and you can imagine what happened when they got about to 25 or 26. All of a sudden, those capabilities, allocating a new capability became a lot harder to do, right? You had to really justify it. So you're a kernel engineer. If I was a kernel engineer, I'd be about as lazy as possible. So I have a new security feature that I want to check, right? A new whatever, not network stack, but anyways, a new feature on it. So how do I handle it? Well, it turns out that there's a couple of very big capabilities out there. So there's Capnet Admin. Capnet Admin allows me to change things like the IP tables rules, network stack, firewalls, create route tables, things like that. But what happens is when we use container runtimes and container engines and container runtimes, we actually can basically pre-configure the network for them. So we don't want the process inside of the container to modify the network stack, so we pre-modify and we can get rid of that. And then there's the big catch-all, which is Captious Admin. So I was talking about that kernel engineer, and he's building a new feature into the kernel, and he says, well, I think an admin needs to do this, so let me look at that list of capabilities. Oh, there's one that has the word admin in it, so I'll use that to block it, right? And this became the huge catch-all. So to give you an idea, these are some of the things that Captious Admin blocks. And up here is one that allows mount and unmount. So if I take away Captious Admin, which is, again, the holy grail of capabilities. Most people say Captious Admin is root. I can actually lock it down. So another page of capabilities, and these are only the ones they list. You can imagine the hundreds that they don't list in the man pages. So we can take away those capabilities, but we still end up with about 10 or 12 capabilities on running as root, including set UID and set GID. And set UID and set GID are pretty important capabilities because you can basically change your ownership to any UID on the system. And why do we need that? Because of the distributions. I installed a version of Apache that I want to make run secure, so it has to go from root to non-root. So if it started as non-root right away, it would not need set UID, but it does because of the way we do it. So the next thing we want to do is we've shrunk the power of root, but now we want to basically start hiding things from the container processes. We want them not to be able to see. And these aren't really security things because it's security by obscurity. But, overall, there's the namespaces. So you think about the PID namespace. When I run inside of a PID namespace, I lose the view of all the other processes on the system. So from a security point of view, people would argue that's not really security because those processes are still out there. But if I can't see them, it's harder to attack them. Similar to network namespace. So network namespace, if I'm in a network namespace, I don't see the other network. So I can't see the other hosts in my environment. I'm sort of isolated. So they're all virtual private networks running inside of it. So the next thing we want to do is we want to control access to device nodes, right? Dev SD0, Dev SD1, all those devices, physical devices in the system. So you don't want those devices to end up inside of containers. You don't want, if I can write to the physical storage on the device, I can probably break out of the container. So in container world, we use Cgroups for this. So this is the device Cgroup. And what device Cgroup does is allows us to specify which devices a group of processes is allowed to use, which major and minor numbers. And so in containers, these are the only devices out of the box that are allowed to be used. So we have dev console, dev 0, so basically all the stuff to handle standard out and standard error type stuff. We also have urandom and random, so you can do crypto inside of the container if you need some random numbers, and T2Is. And that's about it. That's about the only stuff we allow inside of containers. Now you can override this with the -- device, but if you start adding devices to a container, there's probably a good chance you're going to allow the containers to break out. right? So just think about it anytime you want to add devices to a container, what does that mean? We also have the ability to mount images as non-dev. So if I have an image as non-dev, and so basically if I did a pull of a container image from a container registry, when that gets installed, I could put device nodes inside of my image, you'll pull it down and put it on your system, and then if I can get the processes to talk to those device nodes, the kernel might allow it to access. So if the container runtimes mount the containers as no dev, the kernel says, no, that's on a file system that's mounted no dev, so I won't use any devices on it. So next thing we want to do is we protect the devices, we protect kernel file systems, we protected, shrunk the power of root. Now we want to protect the file system. Okay, so at this point, the best tool in the world to do this is SELinux. Yeah, you guys screwed up on that one. All right, everybody stretch a little bit. All right. All right, you don't want to sit in, especially before lunch. Usually I get this after lunch and everybody's asleep, but okay. Okay, everybody sit down. Now you're all SELinux experts. Okay? I've tried to explain SELinux for 100 years, well, probably about 15 years now. So SELinux is just basically a labeling system. Every process has a label on it. Every object has a label on it. And then there's the rules that says that this process label can interact with this file label. And then we have sort of classes and stuff like that. But that's too difficult for you guys. Okay, so let's dumb it down a little. All right, you don't have an SELinux coloring book because my luggage is not big enough to bring them with me. Okay, so I've done 3 different coloring books, 2 of them on containers and 1 of them on SELinux, but I'll show you the pictures. Okay, imagine you have this thing. This is type enforcement, right? This is a really cool thing that SELinux introduced. And in this case, we have 2 processes running on the system. We have a cat process and we have a dog process. Everybody got it? So one's labeled as a cat and one's labeled as a dog. Then we have objects on the file system. So we have cat food and we have dog food. Everybody got me? Stay with me so far? Okay. So now we write a rule into the kernel that says allow a cat process to eat cat food. And we write one that says allow a dog to eat dog food. SELinux by default is deny everything. So if there isn't an allow rule to allow that, then it's going to get denied, just like firewalls. So the cat's able to eat the cat food. The dog's able to eat the dog food. Cat can ask the kernel for more cat food. And then if the dog tries to eat the cat food, the kernel steps in. Everybody got it? That's SELinux. That's all it is. Okay? The problem with SELinux usually tends up that instead of having something labeled as cat food, you have it labeled as Apache data or home directory data or something else, right? But if everything is labeled correctly, SELinux works perfectly. So in containers, this thing's called type enforcement. So it protects the host system for container processes. Container process can only read, execute user files. And basically these are the so container T is what we run containers with. So out of the box, a container is labeled as container T. So the container runtimes always run containers as container T unless the admin overrides it. And then all the data inside of the container is labeled as container file T. All right, that's what the dog food is. Okay, so that means that if a container breaks out of confinement to get access to the host, and it's happened at least twice, SELinux steps in and says, no, you're a container. You're not able to read that user's home directory. You're not able to get access to the database directory. Okay, so basically I'll give you an idea of the 2 container breakouts that have happened. The first one was, turns out there's a syscall called openfileat. Anybody ever hear of that one? So openfileat, you can actually basically say, give me a storage device, and I will just give you an inode, and you will open it. The kernel will open it, even if it is not in my mount file system. So even if I don't see it. Turns out slash, in most operating systems, right, the initial slash is easily guessable. So when people found this, they started using that syscall, and they opened up slash. Now all they got was a file descriptor to a directory object. Then they walked the directory object, got more inodes, opened those inodes, and walked the file system. So as they're walking the file system, eventually they're going to try to open a file system object that SELinux does not allow container T, and it gets blocked. Anybody see a problem with that? With what we just talked about? Right, containers are all labeled container T. All the data is labeled container file T. So everything's a dog. So all the dogs can eat all the dog food. Right? Any dog can eat anybody else's dog food. So what we needed is a separate part of SELinux, and that part is called, the thing we invented back for virtual machines many years ago, called MCS, multi-category security. And this is actually a little more difficult to understand than type enforcement, but basically multi-category security is based on MLS, multi-level security. Multi-level security is incredibly hard to understand, but multi-level security is the stuff that handles top secret and secret information, and it has all these rules. So SELinux back in RHEL 5 time frame, 2006 was when RHEL 5 shipped, and added MLS, multi-level security. So basically, if you look at that SELinux label, the third field is the container underscore T, and then the fourth one, if you've played with SELinux, it almost always S0. But that fourth field is what we call the MCS or MLS field. So what we did with virtual machines and containers and actually original OpenShift is we started picking random MCS labels. And we allowed the tool that was picking the MCS labels to sort of remember which ones it picked. And as long as it picked unique random MCS labels for each one of the containers, we would have the kernel basically say that they had a match. So what we're going to explain that is we now have two dogs. So with MCS, we're able to label the dogs. So we have a Fido dog and we have a Spot dog. We have the dog food is labeled Fido and Spot, and then we basically say that that Fido is able to eat the Fido dog food, and when Fido tries to eat Spot's dog food, the kernel steps in. So the kernel is guaranteeing is that the label, that last part of the label, has to match exactly. So it's picking a random MCS label, and you'll see this is like, well, I'll show you in a second. It usually looks something like this: S0, C1, C2. So using this form of SELinux, basically the container runtime, it picks a random MCS label when a container starts. It labels all the content for the container with that MCS label, and it labels the processes with that MCS label. So this security, as I said, we invented for virtual machines. We sometimes call it SVIRT. And when we talked about the virtual machines being preventive of breakout, we were taking advantage of not only the type enforcement, but the SVIRT. We also did this with OpenShift. So OpenShift version 2, which is the one that's been around since I think 2011, has had up to 2 million users. Each one of those users had different MCS labels. So the MCS labels basically guaranteed us, and we use that to make sure that all of the users of an OpenShift system, right? The only thing you had to do to get OpenShift onto OpenShift was give us an email address, right? Usually the one I use is dwalsh@getlost.com. So basically that, to our knowledge, no one ever had a breakout inside of OpenShift v2. So we use that same security here, and that's how SELinux actually protects the file system. So if a container breaks out, it tries to attack another container process or another container file system, it has a different MCS label, and the kernel won't let them talk. The next thing we want to do, so we protected the file system. Next thing we want to do is we want to protect the Syscall table. So another way you interact with the Linux kernel is through Sis Calls. On a 64-bit machine, there are 650 Syscalls. If any one of these syscalls into the Linux kernel allows you to get access to a bug in the Linux kernel, you can take over the kernel. So if we can cut the number of syscalls down so your process couldn't get access to a potential syscall that would let you take over the kernel, we can make the system more secure. So the tool to protect this is called SECCOMP. So SECCOMP was developed by Google for the Chrome browser. What they wanted to do is they wanted to take all of those fancy GIFs that we all love to see and dancing whatevers and put the codes to actually process those images into a separate process. And then they wanted to take that process and eliminate most of the syscalls so that process could execute. And they did this by developing this thing called SECCOMP. And now I think it's called BPF, so BPF filtering, things like that. So you're able to really take the entire syscall stack that's available to a process and really start to remove those. So we can shrink the attack surface on the kernel, and we can eliminate syscalls. Anybody notice the second syscall up here? Open file, open handle at. That's the one that was allowed to break out. I didn't mention the other breakout. The other breakout was actually If you exec into a container, anybody here exec into a container? When that process execs into a container, if it has any open file descriptors when it execs in, the process inside of the container can attack it through strace and things like that and get access to their open file descriptors and start walking the file system. Okay, so there's been different ways that containers have been broken into based on leaked file descriptors. So basically we can eliminate it in the Syscall table. This is another way that we're blocking it. So SELinux blocks it, actually capabilities now block it, and we block open file at the Syscall level. We also can block 32-bit Syscalls. So the reason is if you went on a 32-bit system, there's 325 Syscalls available. On a 64-bit machine, there's 650. Anybody notice a relationship? Right? That's because a 64-bit machine can run 32-bit code. Most of you probably are not running 32-bit containers on your 64-bit machines. So if we just basically turn on SECCOMP, we eliminate 32-bit syscalls. So any bug in any one of those 32-bit syscalls basically prevents you from breaking out of the container. So instantaneously, we've cut the attack surface in half just by turning on SECCOMP. So we can get rid of these really weird ones, but I know a lot of you guys are using this. How many people out there are using NetWare? DECnet? AppleTalk? How about floppy drives? Okay, remember I talked about the virtual machines, breakouts? One of them was based on the floppy drivers. Okay, how many kernel engineers think you have looked at the floppy drive inside of the Linux kernel in the last 10, 15 years? So that code is ancient. So but basically the Linux kernel never breaks anything. It supports this stuff forever. Right? So all these things are potentially available inside of your Linux kernel. By turning on SECCOMP, you can eliminate things like old weird networks. Okay, so the next one is DAC. This is showing what kind of security geek you are. How many people can tell me what DAC is? Okay, we got one hand, about 3, 4 hands in the room. You guys use this all the time. You don't know what it is. Discretionary access control. I'll give it, it's ownership and permission flags. So it's basically the basis of all Unix systems. So when you run the discretionary access control is baked into the Unix kernel. Really? So you're running as root, and my group is root, and I have these objects on the thing that are owned by root and have a group, and then I have permission flags. That's DAC. That's discretionary access control. So what I really like to do is basically, even though I have root, I'd still like to take advantage of DAC inside of the containers. And the mechanism for doing this is a thing called user namespace. Now, for years, I've been railing against user namespace, but I actually started to like it now. So what it allows you to do is map non-root users into your container, and they think they're root inside the container. So you can basically do stuff like you can take a process, say 5,000, UID 5,000, and say, in this container, you're going to be root. And while you're in that container, you can do root-type things. You have namespace capabilities. So you're able to bind to a port less than 1024 inside of the container. Doesn't that sound like the holy grail of security? And guess what? You've never used it. No one has ever used user namespace. And the reason, well, yeah, but the reason most people, other than this guy in the front row here, unless he's used Podman, has not used user namespace, is that file systems don't support it. Right? So if I say I have a UID 5000 as root, if I'm outside of the container and I look at that process, it says that's UID 5000. If that process inside of the container does IDZ, it comes up and says, you are root. The problem is the file system. If I put a file into that container, the file system doesn't translate it. Because what I want inside of the file system is basically if that UID, if I have a file that's owned by UID 5000, I want that process to look at it and say, oh, that's owned by root. Right? So I want to have basically shifting file systems. And the file systems has never supported that up till now. And that's why nobody uses, right? Kubernetes does not use user namespace. Docker does not use user namespace. Docker uses it a little bit. And Cryo and Docker basically have a little bit of support for user namespace, but they basically allow you to basically use one user namespace. So you can basically say, all my containers are going to run inside of a single user namespace, and that's it. But that really ends up with being everybody's a dog. Right? So all the containers can attack each other. They can't attack the host so well, but they can attack everything because everything's running as UID 5000 instead of running as 0. So what we've done is what my team has been working on for the last few years, and I've been trying to force the storage people to finally fix this, and there's been many, many attempts, but the kernel moves at a glacially slow speed. But basically we've added certain features now that we actually, in user space now, will actually chone the image on the fly. So when you create a container, now you say I'm going to use UID 5000 as my root, I will actually create an entire image with all the zeros remapped to 5000. Right? And that's available inside of Podman right now. Can be used to protect the container from each other. Podman has full support for user namespace. For those that haven't seen any other talks, Podman is our replacement for Docker. It's a command line tool that manages not only containers but also the equivalent of Kubernetes pods, but Podman actually has user namespace in. And what the Linux kernel guys have given us so far is a mechanism to really root these type environments really quick. And there's a new feature that came out in kernel 4.19 that basically makes overlay file system do a really nice job of this. So with user namespace now, you can actually run Podman as non-root. You can do all of container things as non-root. Everything you've ever done with Docker you can do as non-root, and we're making it better all the time, and that's taking advantage of user namespace. Okay, so we've talked about all these things that we do to really prevent traditional containers from attacking the host kernel. So let's get rid of the host kernel. So there's been an effort over, if anybody, again, with the Scott's talk yesterday, we talked about Oci Runtimes. So all of these tools like Podman, Docker, Containerd, Cryo are all container engines, and they all exec an Oci runtime, what I like to call a container runtime. So container runtimes was a standard that was developed, and almost everybody uses Run C to basically do everything I talked about here, setting up user namespace, setting up SELinux, all that type of security stuff. But I can actually swap out Run C for different types of container runtimes. And I can start to, and what's happened over the last few years is companies are starting to develop new types of container runtimes. And the first one they're going to talk about is KATA Containers. And that's a great one for a Boston accent. So I got to explain the Boston accent to you people. Okay, when the word ends in ER, you say A, okay? So I parked my car, AR, you make it AH. So I parked my car. When a word ends in the A sound, you actually put the ER in. So we're just moving them around a little bit. So for instance, I would say the first 3 digits of a telephone number is area code. So we would say area code. So when I say KATA, that would be KATA, K-A-T-E-R. If he spelled it K-A-T-E-R, I would say KATA. So KATA containers. So KATA containers. Why do I do this? So KATA containers. KATA containers is actually used to be called. Anybody here KATA containers? A few. Anybody here a Clear Linux? Clear Linux containers. So or Hypershell. Anybody here Hypershell containers? So Hypershell and Clear Linux. Clear Linux is done by Intel, and Hypershell is done by Hyper somebody. I think it's a Chinese company. So they were a Japanese company. They were working on KVM separated containers. So you're taking advantage of KVM, and what they wanted to do is, KVM has some issues, for slow speed up, right, loading a virtual machine, but they're not loading a virtual machine here, or they're loading a very lightweight virtual machine, and then they're running those traditional containers inside of them. So they can actually run containers with KVM separation. So we basically move the containers into a duplex. Pretty cool, huh? So KATA containers, there's problems with KATA containers because there's issues when you move them into a duplex because they're sharing a little bit of the host operating system. We're working in the kernel teams to fix that. But basically, think about most of the time when you run a containers, you want to volume mount into the containers. You want to volume mount or bind mount in the container. As soon as you're in a KVM separated container, you can't volume mount, you can't bind mount, right? Because you're working with 2 different kernels at that point. So you have to use some kind of network protocol to do it. So what people have done with KATA containers up till now is they're doing, Plan 9 file system or NFS, and obviously that kills your performance. But there's work going on in the Linux kernel right now to fix that, to basically get high-speed file systems between a KVM kernel and a host kernel that don't, rely on real network to, that just because the kernel's smart enough to do it. So that's KATA Containers, really cool. You can run KATA Containers right now in Cryo. For those that don't know, Cryo is our replacement for Docker for Kubernetes environments. If you run containers inside of Microsoft, you run Linux containers inside of Microsoft's operating system, you're using Cryo with KATA Containers underneath it. That's how it is. So if you run in Microsoft Cloud, they're native instances of containers. So Google announced last spring this thing called gvisor. So Google is so in love with Golang, they decided to implement the Linux kernel in Go. And that's what this thing is. So gvisor is another OCI container, and what they did is they basically caught every single syscall. Their goal was to catch every single syscall coming from a process and then interpret it, and sometimes they forward those onto the Linux kernel. But basically, they took SECCOMP and really put it onto steroids. So gvisor came out, and Google is basically saying that they plan on using gvisor to run all their containers inside of their cloud. So any of their containers are going to run inside of gvisor as their container runtime. This, again, issues with gvisor. To me, gvisor probably is not going to, I don't think it's going to perform very well because it's going to be very similar to running sort of user mode virtualization, I think. But Google has some really, really smart guys, so they probably are going to get the performance up fairly high. But for certain workloads, gvisor might be the future. So not to be outdone, this company called IBM that I've been hearing a lot about the last couple of days came out, and I used to poo-poo this, but now I probably can't anymore. Created this thing called Nabla, another good Boston word. So Nabla, or Nabla as you would probably call it, is another implementation of a Syscall trapping OCI runtime that's coming out of IBM research to basically do very similar to what gvisor does. So these are three potential future ways of separating security. Right now, Kubernetes has no way of using user namespace. It has no way of using any one of these containers, but these alternative container runtimes. But they're coming. All these new features are coming to Kubernetes eventually, and that's basically as far as I'm going to go with this talk. It goes on for a few more pages, but I think we've good block here. So at this point, I'll open up to questions, and I'm standing between you and your lunch. So, anybody have any questions?